Go.
All right, thank you everyone. Thanks for coming here, thanks for inviting me here. So I'm going to talk about this paper that Matthias and I put out somewhat recently of quasi-normal modes of electromagnetic branes. And I'm going to stress mostly this last section of this continued fraction method of calculating quasi-normal modes because I think it's somewhat unique and has its benefits often. So, all right, I think we've heard this enough, but I'm going to repeat of just kind of what holography does for us, why we're using it. And so the major thing that I want to talk about is that geometries with black holes in them, holography tells us that these are somehow equivalent to a field theory at some finite temperature. And so this is most often what we're using holography for. And the reason we're using this is because of this strong weak duality that happens is that when things are kind of strongly coupled in this field theory, the gravity is weakly coupled, it's just GR in what we look at, and so it's somewhat simpler, or at least we know how to do the calculations, and so we can do that there. And so this is why this stands in for this quark-gluon plasma at RIC and LHC. Okay, so what I'm going to talk about today is the consequences of, on this side, having some sort of background gauge field. So I'll make this explicit in my examples of what I mean, but you're just thinking of, you don't just have a plasma at a finite temperature, but you also have some sort of either magnetic or electric field or a charged plasma. So one of the most often kind of calculated properties is these quasi-normal modes. So these are, I would say, at least originally, just properties of a black hole. And what they quantify is how this black hole system, which is in some sense a dissipative system, how does it return back to equilibrium? So we can start in some equilibrium and we can perturb it slightly and see how it returns back to equilibrium depending on what perturbation that we made. So these are, I think, all stuff that we've heard so far, but this is often discussed with this ring down is what it's describing. And what this kind of means is that we have modes, but they are not normal modes. So their frequency of these modes is not completely real, but it has some real part and some imaginary part. And these things capture kind of how does this perturbation decay back to the equilibrium and at what frequency does it oscillate. So kind of both of these pieces are quite interesting. So what we're going to specifically study and what we did in this paper and what I'm going to talk about today is looking at two solutions to Einstein-Maxwell theory. That because I'm just going to talk about it. But yeah, so we're going to look at two solutions to Einstein-Maxwell theory and see how these quasi-normal modes change while we change different parameters in the theory, such as the magnetic field or the charge of the black hole and stuff like that. So why I think we were motivated for this and just a good motivation for looking at quasi-normal modes in general is comparing to a lot of what we've already seen, which is these simulations of whatever. The simulations of something happening in a gravity space-time often end up with a black hole forming and it bringing down to its equilibrium state. And so we've somewhat seen that quasi-normal modes are, shockingly describe a lot of this evolution. And so it is important to understand the quasi-normal modes of any equilibrium configuration so that you can then compare it to the end result of a dynamical evolution. Okay, so that's sort of, I guess, was my part one of intro of what I'm doing. So now to get to some details.
And emphasizing this last point further, as we saw in some very nice videos yesterday, the fully nonlinear evolution is approximated at relatively early times by some of the quasi-normal modes.
Yeah. So I think we all think that's pretty surprising and I guess powerful.
Take advantage of that.
Yeah, and so it is certainly good to understand what the quasi-normal modes are from this other perspective of you can start in an equilibrium and perturb it slightly and they tell you how you get back to equilibrium instead of starting completely out of equilibrium and watching the evolution towards equilibrium.
Group this paper together with David. Maybe that's what you want to comment on that. Like that's a nice.
Well, I would agree on this. But yeah. Okay. So this is actually only true if already a black hole forms. So in a constant simulation, if you have two black holes separately, then I think it's not really true. But at the moment there's a single horizon, then I think this story starts quickly. It's a very ancient result by Price and Poulin, I think. Those limit approximation. I was wondering maybe if you could say a bit more about it. You say this background gauge field. I think you mean the background gauge field as a black hole, right?
Yeah, I'll quantify this a little bit. So I'm definitely considering a charged plasma as something with a background gauge field, meaning in essence it has some sort of chemical potential. So yeah, this is certainly more on the gravity side is how I'm explicitly doing it, but you can consider it being true on the field theory side also.
So maybe I was confused, but I thought this gauge field did not correspond to a gauge field in the plasma, right?
What you mean is you're going to take CFT with a global symmetry and turn on the chemical potential or background magnetic field
From some R charge or something like that, right? Or what?
Yeah, I'm doing it pretty bottom up, so I'm just looking at Einstein Maxwell and have some
Well,
gauge
okay, so the gravity part is clear, but I was just wondering how it works in the plasma.
Yeah.
Well, I agree with this stuff, of course.
Yeah, so yeah, we'll look at the two examples is a Rasmussen Nordstrom black hole is charged, and so the plasma has some global charge to it. So it's not, yeah, okay, you're right. I shouldn't call it a gauge field on the boundary because it's not a gauge field, but it's a background field.
I think it's like conserved charge.
Yeah, there's a conserved current, and what he's saying is that he's coupling a background heat. And the problem is, whenever we're talking about ADS CFTs, we have both things in mind. In CFT terms, what he's saying is take a theory with a global symmetry current that's dual to some bulk gauge field, and for that global symmetry current coupled to a background gauge field that implements chemical potential or external magnetic field.
Yeah, so maybe on this I shouldn't have left out these words. We have some background fields, and it's either the fact that there's a chemical potential and a charge or a magnetic field. Okay, so we've seen a lot of this so far. We've seen this Einstein piece for sure. I'm going to, I think, as everyone's talked about so far, look at this in a 5-dimensional bulk spacetime. So we have Einstein-Hilbert and cosmological constant term, and then, okay, I guess actually I am doing this more top-down because that fixes what this is, but I also have the normal gauge field piece of the Lagrangian. So yeah, so this kind of the normalization fits in between gravity and electromagnetism. This comes from some kind of consistent top-down approach to it. So as we know, for cosmological constant being negative, you're going to have this whole slew of solutions that are asymptotically ADS. So the first one I'm going to look at that we at least have heard from flat space is some kind of Reisner Nordstrom solution. So so again, as we've seen, you can always kind of work in either some sort of global ADS or some point array patch, and I'm going to completely talk about point array patches. So I'm really doing, doing branes and not holes, things that have this translation symmetry. So in the Reisner Nordstrom case, this is some sort of charged black brane, and has a radial electric field coming out of it, which is dual to a charged plasma. So I'm just gonna, I guess, in this case, write down what the solution is because it's fairly well known. So this kind of expression captures, I guess, a lot of black hole solutions. So for me here, this R is this bulk radial direction. R infinity is where the boundary is. And then here is kind of, the field theory directions, the T and three spatial dimensions. For Reisner Nordstrom, this blackening function is given by this. So yeah, here and also above this L is just what your ADS space curvature is near the boundary, and you have the two parameters kind of controlling this, the mass of the black hole and then also its charge. So the L I'm going to more or less ignore as we often do in essence. Just set it to 1, or you can just see, you can always redefine quantities that L just completely scales out of all your equations. So the horizon of this black hole is at whatever the largest root of this equation is, and I'll call that RH, although we'll also often scale that out. And then yeah, Q is a charge and is limited by this kind of extremality condition that for fixed M, there is a limit on how big Q is before kind of two roots of this thing coincide and you are at a 0 temperature. I guess I'll write this here because I'll probably use it. So Q needs to be less than this extremal value, which in these coordinates is square root of 2 times some function of the mass. All right, so this is the solution for the metric in here, but we also need the solution for the gauge field, and as I already sort of alluded to, this solution has a radial electric field. So we can write this as the gauge field being having some constant part and then some radial independent part that depends on charge. So this mu here is just some constant, and then the dependent part gives you kind of the electric field that's needed to support this. So we can do, a lot of our normal things with this, and for example, look at the near horizon behavior to this, and we often do this in some sort of Euclidean change of this metric, and from these things we can determine what the temperature of this black hole is. So I'll just write down these properties. So RH is this horizon radius, the biggest root of F. So our temperature ends up being related to that, and we can also look at Polyakov loops of this gauge field and see that this constant mu, which you would think is irrelevant because it's just a constant in your gauge potential, actually needs to be fixed to a certain value for everything to be regular. And this is why we end up calling this thing often the chemical potential because it's somehow related to the charge of the system. Okay, so this should be at least somewhat familiar or reasonable in terms of thinking about, you know, I could if I changed F, this could have just been a Schwarzschild ADS black hole, or we know Riser or something flat space, and I'm just adding these kind of factors to make it ADS. One useful thing that we have done a bunch so far is in these coordinates, the boundary of ADS space is at r equals infinity, and it's somewhat difficult to do numerics on an infinite domain like that. So we would like to change these coordinates to, in essence, u is some kind of inverse of r. So I'm going to actually define a new coordinate, a new radial coordinate. U is RH over r actually squared. So if you kind of look at the metric, at least you'll see it only depends on r squared. And so this can be a reasonable thing to define that it's squared, and it will simplify a lot of our equations of motions and stuff like that. This is also useful because now the horizon, which is at r equals RH, is at u equals 1. So we're most of the time interested in this domain between the horizon and the boundary, which is from u equals 1 at the horizon to u equals 0 at the boundary, where r goes to infinity. Okay. And sort of just from looking at equations of motion and stuff, you can see that there are additional rescalings you can do to simplify this. So one of them is to rescale the charge that I expressed there by some power of the horizon radius, and then also rescale the time and the spatial coordinates x, y, and z in the x vector. And the reason to do this is you end up with a metric that doesn't explicitly depend on RH at all. So you can, in essence, scale that out, as long as you also make use of this fact that now in these u coordinates, the horizon is at u equals 1. So this f function at u equals 1 should be 0, and we use this to determine what m is in terms of q. So now the metric only depends on q is kind of the only parameter that's in it. You don't have RH, you don't have the mass, you don't have the L. Okay, so we can sort of just do a very standard holographic analysis to this to see what the stress tensor of the dual field theory is. So I'll just kind of write down that it, has this energy density that corresponds to the mass pretty expectedly. And there's some pressure to it. So we can look at this and see from the field theory side, right? There's one time dimension in these 3 spatial dimensions. So if you kind of take the trace of this corresponding stress tensor, it ends up being 0. This spatial or this temporal piece plus 3 times the, or I guess minus the temporal piece plus 3 times the spatial piece. So this is just a result of the field theory still has conformal invariance because this is asymptotically ADS. Okay. So this is all under, I guess, my bullet point 2 there of looking at a background, right? Here we have some Blackwell or a black hole solution to our theory, and now we want to look at how do perturbations of that decay back to it. And so this is kind of this definition of quasinormal modes. We'd like to see how these perturbations relax back to equilibrium. And a very important point is that different perturbations of both the metric and the gauge field can couple to each other depending on what background we're looking at, so in this case we're looking at Rising Nordstrom, so depending on the background we're looking at, and then also depending on kind of the symmetries of the perturbation that we turn on, whether it has, you know, translation symmetry in the T direction, for example, or one of these spatial Y directions. So one thing that we're going to look at for this solution and also the next one is this, I guess people will call this the shear fluctuation. Is we'll look at this a metric perturbation in the XY direction, two of these spatial directions, and we can see that this completely decouples from any of the other perturbations of the metric or the gauge field. And if I make this kind of useful definition that the perturbation is some field phi that depends on R. Okay, this is
Stefan, can
Yeah.
I ask you a quick question? I think it's a stupid question, but I want to answer anyway. I'm confused why generically in a generic solution that has both a temperature and chemical potential, why the stress tensor, the trace of stress tensor should vanish, because now don't I have a dimensional scale that's important from a field theory perspective, the ratio of those two?
Yeah, so I mean, you would think you'd have a scale to it, but that's in essence the state that we're looking at, right? So on sort of an operator level, the field theory is still conformal.
But if I evaluated it in a state that has a chemical potential and temperature.
Right, so the issue there, as we'll see with the next example, is that the chemical potential isn't breaking this conformal invariance. There's no anomaly associated to the chemical potential, whereas there are anomalies associated to a background electromagnetic field. So this isn't generically true. This is true in this state that we're looking at, in this black hole we're looking at. So yeah, I mean, you're right that I think just on dimensional grounds you might not expect this because there are some kind of scales to the theory, but you need to do some more work to see whether these things you introduced are actually related to conformal anomalies or not.
I mean, there's two possible sources for a trace. One is an anomaly, and the other is just
Some explicit breaking.
And the statement is right, is that for vector operators, there is an analog of the beta O term. It can be on the right-hand side of the trace, but actually it's, you get that means the beta functions are non-zero for vector operators of dimension above the infinitary now, above that of the conserved current.
It's important that it's conserved, that's the
fact that it's conserved, another way of saying it is that under the theory is still violent variant, but up to anomalies, as Stefan was saying, for any configuration of the AMU, but because the AMU doesn't transform under violent, you still retain the violent variance, and so you still have the usual violent word identity.
Yeah, let's see. So yeah, so it's useful to define this metric perturbation in this way. In essence, I'm just kind of stripping off the boundary behavior, the radial boundary behavior. So I guess okay, this is a U1 sum. And so looking at this, you can in essence see that what I'm really doing is defining phi as delta G x y with one lower and one upper. There's various ways to see this is often a good thing to do. One is like I said, you can just look at the equation of motion for delta gxy and see that near the boundary it needs to go like 1 over u. So why not strip off that divergent piece that you know of, or that divergent behavior that you know of. Another way to realize that this is the phi is a good field to look at is looking more at a kind of gauge invariant field and not just some component of your metric, and you'll see that that corresponds to phi and not gxy lower. All right, so I've mentioned quasinormal modes a few times and how they relate to some perturbation around a black hole returning to it, but I haven't quite defined them, so I'm going to do that now. So what you want to do in practice is look at, take this metric that I had there, this solution to Einstein-Maxwell, and plug in, oh, okay, that I have some perturbation to the GXY component. You can either plug that into the action or into the equations of motion, the general Einstein equations, and then linearize them around GXY. So you're just finding kind of this first order behavior of these perturbations. So doing that in this case, which this will be useful for the problem session, so I'll probably write it later, but I'll write it now, is just what is the equation of motion of phi? What does phi have to behave because of Einstein's equations? If it's some second order linear ODE. Which in the U coordinates looks like this. And what I've done here is assume that this perturbation, I guess, yeah, I should have mentioned it earlier when I'm saying that this perturbation does decouple, is that this perturbation, I've kind of Fourier transformed it in time and also the z direction. So there's some sort of frequency to it and some sort of momenta k in the z direction.
Stefan, is it, out of curiosity, I mean, back when people were doing all the Quasinormal mode computations, actually from Seattle in the early 2000s, they were all using the standard Schwarzschild coordinates for the black branes. But there's other problems like gravity or nonlinear evolution where the ingoing and incoming is much easier. What happened? Like, did you guys ever, like, is it more advantageous to do the Quasinormal computations in Schwarzschild as opposed to ingoing and incoming?
As far as I'm concerned, it was just traditional. No, I think that actually it might be nicer in adding Finkelstein because you only have one derivative and a few nice advantages. But
There's
Also
also,
to select the ingoing or the future horizon.
so
Yeah.
historically, like also in stuff like that Gary Horowitz and Ron did the Quasinormal ones before, they also use that Finkelstein coordinates exactly for this reason, especially like at zero temperature. I guess if you want to have the right notion of the ingoing, because I guess we'll talk about the boundary conditions that are really important when you're defining
For zero.
Quasinormals.
I find things a little more intuitive. I don't know what your feeling is about it, but in the background, I don't know. Yeah, it's
I'm just curious. I mean, yeah.
But you're right. Some problems I feel are much better attacked in Eddie Finkelstein. I had a feeling it didn't really matter in our case so much.
Yeah, I certainly agree with that. It doesn't super matter. You can certainly look at it in either case.
But I think the coordinate singularity at the horizon now in these coordinates?
Yeah. So this f function vanishes at the horizon. So this tells us that this differential equation has these singular points wherever f does vanish, and also at the boundary that u equals 0. Where these
Isn't that something you have to deal with?
Yeah.
You have to deal with it.
In that Finkelstein, you don't. You do it.
He knows in this case how to set the right boundary conditions at this radius. If you didn't have that to guide you, maybe then you could use it and Finkelstein and regularity, which would do the exact same thing.
Right. It's
If you know what
regularity
you're
on
following
the future
it.
horizon. You can, I mean, if you set up nice initial data, then you set up numerical evolution to do this. But if you do fluid gravity, for instance, then the regularity on the future horizon is a natural boundary condition that you have to impose. And the fact that you have an irregular solution implicitly tells you that the future horizon is a singular point of the differential equation against the conditions.
Yeah, so I mean, maybe this is actually more useful because it's very explicitly making clear that there are these singular points at the horizon, and so we need to apply some boundary conditions there. So yeah, so this certainly directly leads me into what my definition of Quasinormal mode is, which I'll abbreviate like this. So what I have here is the equation of motion for some perturbation around a solution of gravity, and in this case also Einstein-Maxwell. And so a Quasinormal mode is a solution to this equation that has these two boundary conditions. So one is that it is infalling at the horizon. this in essence determines some sort of sign in the characteristic exponent. So what you can do is take this equation and say, okay, near the horizon there's some power series, there's some solution to this that behaves as, you know, the horizon's at u equals 1, so it's 1 minus u raised to some, just write this down. Right, near the horizon, this phi field is 1 minus u raised to some power plus corrections to that. And so this infalling boundary condition determines what that power is when I recombine this solution with the fact that I've Fourier transformed it in time. Right? So there's some e to the minus I omega t, and so I can then look at, you know, follow constant phases and see whether something is going in or out depending on the sign of delta. So that's one thing, and then the other thing, right, is second order. We need two boundary conditions in some way. And the other one is that it's Dirichlet at the boundary. Which is, again, u equals 0 in these coordinates. So I think this is just one way, you know, I have a generic equation of motion, and I'm defining Quasinormal laws as solutions to the equation that have these two boundary conditions.
Dirichlet, or is it just their phi is regular? The way
It's normalized.
I mean, phi.
Yeah, so that depends on the perturbation that you're looking at. So in this case, since
This is a generalized notion of Dirichlet.
yeah, okay, sure. So yeah, maybe this is specific to this certain metric perturbation, but
I mean, in this particular case, you've selected out the normalizable component of the normalizable xy. Sorry, if phi is order 1 and u equals 0, then that corresponds to there being no non-normalizable term for gxy, and there being a non-zero normalizable term, right? So the boundary value of phi is the normalizable component of gxy. So for what you're doing, it's the boundary condition is that phi is regular and u equals 0. Is that right? Following your definition.
yeah,
I'm not sure what
yeah. I mean,
Dirichlet is that the field is 0. That's
which
assumed.
is true
yeah,
here
that's
because
what you want here. Yeah.
I mean, phi equals 0.
Yeah.
Isn't phi the 1 over arc or sorry, 1 over relative
Should be
to
arc,
the leading r squared? Is there the 1 over r to the 4 term in the?
You can do the same thing that Stefan suggested, with, but u to the delta, right? And then you get two
I'm
powers
just saying
at
on
the
the
boundary.
left-hand side, the way that he's defined it. The way he's defined it is the metric, the boundary
Okay.
goes as r squared times g boundary. And if I expand it out, if I from a gram g boundary in inverse powers of r, then the leading order term, which would be like phi going like r to the 4, that's like a deformation to the boundary metric, right?
Could I ask for a clarification? What if he factored out just 1 over square root of
Yeah,
u?
exactly. I think
Then
that's
you could-
the sensor which is Dirichlet. Is that
Yeah.
you factor out the leading fall off and your field is the rest of the stuff and it's Dirichlet on that, on what's left. Right? Because then if there's a source term, it goes like constant.
No,
You're setting that to
I guess
0.
what Kristen's
Yeah.
pointing out is he factored out all of the powers already. So it's the coefficient, that's actually variant, that's a dynamical thing. You're not allowed to set
This would be
it
like setting the variation of the stress
Yeah.
tensor to 0.
Yeah, so that's, I mean, like, maybe it's just a typo or whatever, but you probably wanted to factor out just one power fewer such that it still falls off to 0.
U is 1 over r squared. Does that help?
U is 1 over r squared.
Or rh squared over r squared?
yeah. So I think
okay.
where you're thinking I think you're more thinking of gxy. So gxy, I'm demanding that that's regular, but in the way that I defined it phi, it means that phi is 0.
Yeah, that's
Okay, so in practice, what you're doing is you're saying that the variation of gxy is normalizable.
Yeah.
Yes, that's good.
Yeah, we can all, okay.
So
So whatever the definition of U is, it's accomplishing that.
Yes.
Okay.
So just as a clarification, then what you've done is you've killed the other non-normalizable piece. Is that right? That's the boundary condition.
That's this boundary condition.
Good.
Yeah. So this, I mean, phi itself could be some finite value at the boundary, and So GXY could be divergent at the boundary, but I want to look at modes that phi is 0.
Okay.
Let's see. So, okay, so this like looking at normal modes of a system is I have some equation of motion, I'm applying some boundary conditions to it, that this will only hold for some discrete values of your frequency. So these frequencies are called as quasinormal mode frequencies. And so I'll often use the idea of quasinormal modes in this sense, a solution to this equation, and quasinormal modes as what is the frequency of this specific solution. Those things interchangeable. We'll call those both just the modes. So one is the frequency of the modes, and one would be the actual solution of the perturbation. Okay, so I'll talk about shortly one way, well, I guess very shortly, one way to solve this, and then in more depth a different way to solve it. But I'd first like to set up the other background that we deal with. This was all looking at our background solution being a Reisner-Nordstrom ADS black hole. So the other one is what are referred to as magnetic branes. So the Reisner-Nordstrom one had some kind of radial electric field, which you can see is dual to a charged plasma. What we're going to deal with now is an uncharged plasma, but has a constant magnetic field, in this case parallel to the horizon. So that means that the dual field theory has a background magnetic field, and I'm going to just choose the z direction. Okay, so in kind of these same u coordinates, we can make an ansatz to the metric. This is really just based on symmetries. We've seen a couple of different ansatz depending on the symmetry we're looking at, and what I'm going to do is say, so here's my time and my radial piece, and then there is some should explicitly write this out. There's some component in the xy directions that are still symmetric, but there's allowed to be different behavior in the z direction because that's the direction I'm going to have a magnetic field. So at this point, this is just an ansatz kind of capturing the symmetries in some Schwarzschild-like radial coordinate. This is the metric background, and then we also need to look at what the gauge field is, and I'll just define that by what the field strength is. So there is just a constant fxy that I'm calling B, and so this is, you can think of as a magnetic field in the z direction.
So that works globally, that applies globally, this field strength?
Yeah, this is everywhere in the bulk.
The interior as well?
Yeah, so B is constant, doesn't depend on my radial direction u, but this field strength is everywhere in the bulk.
It's a solution.
Yeah, so at this point, this is just an ansatz, right? I need to tell you what all this u and v and w functions are. So you can see that this is a solution to, in essence, the Maxwell equations for whatever those u and v and w's are, and so that's kind of a start. And unfortunately, unlike what I could write down for the Reisner-Nordstrom case, is there is not an analytic solution kind of known to this system. So you need to numerically determine your background. You need to numerically solve for u, big U, and v, and w. So kind of the way that this is done is we'll sort of start at the horizon, right? We'll define, still in these coordinates, we want u equals 1 to be our horizon. And in essence, we'll start saying u equals 1 should be a horizon. And what this means when you look at this ansatz is, well, let's expand this big u function near the horizon. It has some kind of power series demanding that u equals 1 is a horizon means that GTT, in a rough sense, means that GTTs should vanish. So that means this U0 should be 0 at U equals 1 because we want there to be a horizon. We can then also look at the expansions for these other functions. So V naught also has some expansion, as does W. And in this case, simply just because of how they balance us, these things are these exponentials, is that, you know, at the horizon, V and W are just two constants, V naught and W naught. And so if you look at the metric at the horizon, there's just a constant out here and a different constant out there. And we can just get rid of those by rescaling X, Y, and Z. So that means whatever this constant is, we can just set it to 0. We can rescale so that at the horizon, this metric is just dx squared plus dy squared plus dz squared. There's no factors up front. Okay, so this is sort of kind of a power series that we, you know, make this ansatz that are these functions are power series near this horizon. We then look at what Einstein's equations or Einstein's Maxwell equations, how they restrict these, and we'll see that, you know, all of these U, V, and W, and there's just further of these in expansion, that the rest of them are determined in terms of just this U1.
Is it obvious that this V0 and W0 are the same?
So that's just a gauge choice, really, right? So generically at the horizon, you would say V is some constant and W is some constant. And so let's look at my metric. There's some constant times dx squared plus dy squared.
Usually you wouldn't just rescale X and Y and Z differently, right? Because
Yeah,
the boundary, then you screw up your boundary.
Yeah, we'll definitely see that by rescaling these things at the horizon means we don't have the freedom at the boundary to say that it is this kind of canonical Minkowskian.
If that fixes the X, Y, Z squared anyway, you cannot do it both at the
Yeah.
boundary and at the horizon.
Yeah, I agree.
It's
So-
good.
So I'm doing it here. So there's two ways to do this. I can either say I'm going to start with my initial conditions being that there are two constants in this V and W, and those are constants that I need to vary to get the boundary expansion to be just 1 over U.
Right.
Or I can say I'm going to rescale my X and Y to set these constants to 0, and then my boundary expansion is, you know,
Okay, so
some
your boundary
constant.
matrix not minus 1, 1, 1, 1.
Right. Yeah.
It's different.
But I don't think this is a problem, right? Because and this
No.
is a trick, because you can do this in the IR, at the horizon. You obtain some boundary metric, and then you just rescale it.
Just
into
rescale
some
that.
fiducial form,
Yeah.
some canonical form for comparing different solutions.
Like,
As long as you do this, it's no problem. It's just to make life easier.
Yeah. So yeah, I'll certainly show that pretty explicitly. So, but yeah, just to be clear, these are two very different things. The fact that U naught vanishes is me saying I want there to be a horizon at U equals 1, and then the fact that V naught and W naught vanish is me in essence making a gauge choice. I'm rescaling my coordinates so that in X, Y, and Z that I have here, that at the horizon the metric is just dx squared plus dy squared plus z squared.
Why is it convenient? Could you not have just applied that condition in the boundary?
So, I mean, it's somewhat convenient for a numerical integration, right? If I left these things arbitrary, then what I would kind of have to do is vary V naught and W naught until my boundary metric is kind of canonical. Instead, I can just set them to 0, like Chris said, integrate out to the boundary, and then whatever their value is there, then just kind of divide by them, and it tells me what was the correct V naught and W naught to have.
Stefan, in terms of this near horizon expansion, what choice of initial conditions do you need to get the extremal limit?
And then the U1 vanishes, I think, right?
Yeah, so I'd want U1 to.
Because then the dt squared and the du squared and u all got to be singular.
It has to be double root at, right.
I don't think this one, I mean, this delta, for example, goes like 1 over t, right? In the part that you factor out. So then you have to look at the equations directly, s equals 0, right? It's some power law.
Yeah, so I think for t equals 0, you can make a slightly different ansatz in which I think you sort of alluded to this, is that this w function is then directly related to u. This is just u also.
So to capture non-extremal, this is the Iconian thing to do, an extremal.
Yeah, you would kind of make a different ansatz.
Extremal gives me S3 cross R2.
Yeah.
Horizon.
Well, these structures allow for that, right?
Yeah, they do, but then the analytic structure would be rather different.
Well, the same, you want to be 0.
Either the two W that has to be singular as opposed to regular. The DZ squared makes up an ADS3 along with DT and DU.
Yeah. So
du squared,
DU, DT, I mean, the near horizon is ADS3 cross R2. It's like the conformal field theory dual to the lowest lambda level of the equals 4 non-zero magnetic field. So DT, DU, DZ all make up an ADS3. Correct me if I'm wrong.
no. Yeah.
It requires either the two W to be singular, which is not captured by the, not within the set of boundary conditions.
Yeah, so I mean, maybe I should talk about kind of how we expect these solutions to behave in different limits of B, right? We know that for B going to 0, we should just have the Schwarzschild solution, right? That's just, there is no electric field or magnetic field turned on, and so this should just be the Schwarzschild solution. You can then see that in some extremal limit in t equals 0 limit, one solution that you have is what Christian's saying, is that the TU and the Z direction form just an ADS3, and then this is in essence just a torus or a plane, I guess. And except that, yeah, so the issue there is that's a solution to this, an analytic solution you can show, but it's asymptotically is not ADS5, right? It's still asymptotically is this product space. But you can still understand what the near horizon geometry is going to look like. Is in a small B limit, it should look very much like Schwarzschild, and in a large B limit, it should look like this ADS3 cross T2. Okay, let's see what was looking at. Okay, yeah, so I was saying, you know, near U equals 1, we want to demand that's a horizon, and so for an expansion of these functions, we can determine that these leading coefficients either need to vanish or we can set them to 0 by coordinate choice. And then the rest of these U, UI, VI, and WI, these are all determined in terms of U1 and B. So in essence, well, I guess, did I write this down already? Well, yeah, so the kind of the same formula that I wrote down for the Reisner-Nordstrom holds, and you can see pretty clearly that U1 is just related to the temperature. So yeah, U1 is just 2 pi t, these coordinates. And B, as we'll see, is related to the magnetic field that the field theory sees. All right, so this is just kind of examining this ansatz and Einstein's equations near U equals 1 that we want to be a horizon, but we also want near U equals 0 to be a boundary. We want near U equals 0 for it to be asymptotically ADS. So the first thing that we kind of see is we still need a cosmological constant. We need the same cosmological constant that is in just normal ADS and also this Reisner-Nordstrom ADS. And so once we have that cosmological constant in our equations of motion, we now have some near horizon boundary conditions. You can numerically integrate these out to the boundary and see what the values there are. So kind of generically near this boundary, so as U goes to 0, these functions are going to have this behavior that the big U function goes like 1 over U, our radial coordinate, and this is really just this demand that it is asymptotically ADS. And then there's sub-leading corrections to this, and importantly, as we know, there'll be some kind of undetermined vev just from the near boundary expansion, which comes in that coordinates that order used. This is kind of a sort of sourcing vev. As Vilka was saying, due to what I did at the horizon, my rescaling of x and y at the horizon means that near the boundary, this v and w functions don't just go like 1 over u, they go like some constant over u, because I rescaled these coordinates here. So what this means is to do, right, to look at dual theory or dual quantities, we want our boundary metric to just be Minkowski. We don't want it to be -1 VVW. We want it to be -1 1 1 1. And so we need to rescale the metric now by this V and W. So the main effect of this is that since our field strength was this, right, it was B dx wedge dy, I'm now saying I need to rescale dx and dy so that field strength is really B over V dx hat, dy hat, where x and y are my rescaled coordinates. In essence, they are the boundary coordinates. So this is just saying that B isn't exactly my boundary magnetic field. It's B over V, whatever the boundary value of this is. Okay, so yeah, as I mentioned in the Reisner-Nordstrom case, we can do our normal near boundary analysis of the metric to determine what the stress tensor is. So this is kind of generically looking at it in the spectrum in gram coordinates. So this is, I think, another R coordinate that I'm defining here, so it might be a bit confusing, but we're just saying we know that we can pick coordinates where the metric has this form. So it's in essence just some series in R near the boundary. So my mu and nu coordinates are just field theory coordinates, t and x, y, and z. And this R here is a spectrogram R, which you can see as, you know, GRR is just 1 over R squared, whereas up here my radial metric component had some other behavior to it. Okay, so if near the boundary I converge to these coordinates, then we know what our stress tensor is. This was, pieces of this have been discussed already, so I'm going to write this up here so it's easier to see. But from this, we know that our field theory stress tensor is given by this. So it's depending on this kind of fourth component in the near boundary expansion, so these things just depend on field theory directions, not radial. And this is, I would say not a generic expression, but I've used the fact that for flat boundary G2 actually vanishes, otherwise there would be G2 terms here also. Okay, so one thing that we see is this log piece and this appearance of this H term, which came from the fact that they're the log piece in the near boundary expansion. So this is due to the fact that since we now have a magnetic field, there is a conformal anomaly. We don't have this exact scale invariance to our metric because of this log term. So the lambda in here is kind of some sort of renormalization point where we're deciding to, you know, put our boundary, and then C is reflecting the fact that, you know, we can move where that boundary is. So there's some kind of, if we send lambda to lambda prime, all that does is shift this by some constant. So these are sort of constants that we need to fix, and a good way to do this is to fix lambda to be square root of b. One way to think about this, I guess, is b, or I didn't define b sort of here. This is B, little b over B. That's our boundary magnetic field. What I think a physical way to think of this is this sort of the only scale that we have in the boundary. I mean, we have temperature also, but there is this magnetic field. Another way to see that it's useful is to look at properties of the stress tensor and see that in this case there is some sort of there's still some sort of scaling symmetry. Our stress tensor now only depends on ratios of B over T or B over T squared. And then what we're also going to choose is that this constant C is just -1/4. And so what this is doing here is saying, you know, our energy density, there's some magnetic field, so the energy density should be like B squared, right? The magnetic field has energy density to it. So this choosing C to be this kind of subtracts that piece to it. So we're getting rid of the explicit B squared in our energy density.
Did you guys add the f mu squared log lambda counter terms?
Let's see.
For what that you, where would you want to do
So yeah, I mean, so right now this.
log divergence in the stress tensor, and that has to be canceled in the usual way. I mean, if you put the theory on a sphere, then you have the same even dimensional CFT on a sphere. There's also a log divergence in the on-shell bulk action that's canceled off by adding a. I mean, at the end of the day, the effect is the same as what you write when you add a log term. It goes like it explicitly depends on the lambda cutoff slice, but then with an energy scale that you introduce in order to define the theory, just as you say, you have to introduce the scale, and then evaluate the stress tensor at that scale. But I'm just wondering if you guys did that.
So, yeah, we didn't explicitly work out kind of the renormalization of this. This was just taking from
So you
John
took
Miller's
the
paper.
like Skanderis et al. Formula, and then
You can't use that, right? It's not just not applying in this case. There's a term missing.
right because you have a background field strength.
Yeah.
So then you adapt that,
Mm-hmm.
but then okay,
We thought about that, and it's
you adapt the log term.
right. There's basically John and Larry did that first, right? And we just convinced ourselves that's right. So I think that's the right way to give credit.
I mean, it's not when I don't think it's right, but I'm not.
What's the problem?
Well, it's not. Well, let me make a more a less controversial statement. It's not what you do for the other anomalies, for the Biot squared and Euler anomalies. There you add logarithmic counterterms on the cutoff slice in order to cancel those divergences. But I mean, at the end of the day, I'm not sure that the expressions, the final expressions that you get, if they differ by anything, it's really that different from what you're saying.
Yeah, we didn't do this explicitly, so I don't know if this is coming from a counter term that's f squared or a counter term that is just geometric.
I mean, it's just f, on the bound, it's like the f mu with projected indices to the boundary squared times the volume factor of the cutoff slice times log lambda mu, where mu is some scale that you introduce. But the net effect of that is you cancel off like the lambda that appears here, but then it's replaced with the mu, which is the scale that you introduce.
Yeah, so I think that's
So the
the
net
fact that I
effect-
have the C and this one here is.
Maybe the factor form is A swing up, would that be different? Is that what you're saying?
I believe so. Maybe.
Like, how did you get this formula? Because if you just look at the original holographic normalization, they don't have the field strength, right? So you actually do need to redo the whole computation, right?
Yeah, so we looked at people who did redo that computation in that case.
And how did they get the formula? They did the proper frame.
Yeah.
Terms.
Yeah.
That's right.
But that is correct.
Well, I mean, to get the correct formula with all the counterterms, you need to have the logarithmic counterterms.
But they say that some people did this.
They didn't, though.
Yeah.
They have a new counterterm, that they have a new structure. I mean, how to say,
No,
the way you solve for
this
the,
is measured by Larry John, right?
Mhm. Right.
And, well,
when
you just claim that it is correctly, right?
Pretty much
Yeah.
that's what we do,
You claim that
Well, no, I'm asking what these guys did, because they haven't read their paper carefully. And if they didn't add a logarithmic counterterm, then they're following most of the steps of holographic normalization except for one.
But I think you have to do that. I think that's how you get the new term.
Okay, so
Anyway,
yeah, I don't have much time left, so I want to kind of wrap up here, but yeah, so let me just say, we can say, yeah, we took this from other people, but I think they did it by doing appropriate renormalization in the situation. One interesting thing to see is if you look at how, you know, these G expansion, GU, G0, G4 are in terms of our U, V, and W functions, that the trace of this stress tensor is no longer vanishing. And so in this case, this is sensible because we know that there is some anomaly when there is a background gauge field, right? This is like the gauge field strength squared. So this is to be expected and gives you the correct anomaly coefficient. There's a couple minutes left.
Like 2.
Okay, so I'm going to, I guess, well, okay, my next section is results anyway. So I have a small section here of the computational methods that we use. So I think what I'll do is just say this normal method is what's called a shooting method. And so what you would do then, which I think I kind of alluded to, right? I showed explicitly in the Reisner-Nordstrom case the equation of motion for perturbation. And so in the shooting method, you say, near the horizon, I want this perturbation to be infalling. I explicitly apply that boundary condition of the Quasinormal mode, and then I integrate out to the boundary. And what I need to do is then do that a bunch of times while varying this frequency omega. That's kind of the only parameter that's left in my equation. And so I vary omega until I see that the boundary value at the boundary is the Dirichlet thing that I wanted. And then I know that that omega is the Quasinormal frequency. So I think that's a very standard way of doing it. The other method that we did is by using these continued fraction methods. And so I think I will more explicitly go over that once we get to the problem session. But let me just quickly kind of state our results. So they're not, well, okay, part of them is something new. So for the Reisner-Nordstrom Quasinormal frequencies, so what I'm going to just show is just a plot of the Quasinormal frequencies. So for Reisner-Nordstrom, we have, again, some complex omega giving us this ring down of this black hole. And we have these kind of very, very expected ones is there is this quite linear distribution of Quasinormal modes going off like this. We have a negative imaginary part that shows that these things are actually decaying and not growing. And then the real part is kind of giving you their frequency. So this is, it's seen in almost all cases, I would say. What we can then do is we can fiddle with our parameters. So we can either change, this is kind of say, let's say momentum equals 0. We can change our momentum and see how these things move around, and the other parameter we have in the Reisner-Nordstrom cases, we can change Q, and so we can change the charge. So if you change the charge, you see that these things kind of move like this, more or less. They kind of go down and to the left, and right to the right. So this is kind of as Q varies, they follow this trajectory. So that's, I guess I would say, typical, or you change your parameter and you can just follow these modes around. What seems a bit unusual, although it is seen in other cases, is that as we change Q, as Q gets large enough, not only do these modes here move around, but some additional modes come up this imaginary axis. So you end up seeing that at large Q, there are just some purely imaginary modes on the axis here.
Is this the zero temperature limit?
No.
Are you approaching the branch credit for AES2?
Yeah, so this is the large Q limit, which you can also think of as zero temperature, right? I mean, there's this ratio of Q over T. So exactly, that's our sort of thought about this, that's what these things are doing, is these normal quasi-normal modes are going away in this extremal limit, while these other ones are coming up and kind of condensing here to form this branch cut. So just to, I mean, the numbers aren't super relevant, but the point where this first quasi-normal mode, normal one, and these imaginary ones where they're about the same as when Q is like 0.65. And that's where these ones finally come up and you start seeing them. And then for larger Q, the most real one, the one closest to the real axis is actually one of these purely imaginary ones. This is for the Reisner-Nordstrom case. For the magnetic branes, it's maybe a little less interesting, is that we just have, you know, these typical ones going off to the side, and you can do the same thing. You can change the B parameter and see how they move. Well, we didn't actually do them at finite momenta, but you could also do that, is work it out at finite momenta.
And if it comes up, I understood the extremal limit, is it 0 or
These?
Yeah, so
Yeah, they seem to be moving there. I mean, we can't get.
But it goes to 0, so no oscillation at all, or?
Yeah, well, so there's a bunch of these here, and they're all kind of moving up, and the idea is that in that limit, there's a kind of a branch cut along this axis where all these poles somewhat coalesce.
Stefan, can you remind me, do you turn on a momentum? Or are you just looking at the quasi-normal modes at k equals 0?
I think, I mean, as I do this for Reisner-Nordstrom, it's k equals 0, but we turn on momentum, and I think these things are still there. Did we do?
I'm more curious for the black
Here at
brane. You
finite
can have like two different, in principles, two different spatial vectors, one being the magnetic.
Yeah, okay. So yeah, we only looked at modes where, in the magnetic case, where the momentum is in the same direction as the magnetic field.
Okay. And you see, so I guess then do you see that the zero modes, the shear modes are gapped? That they become cyclotron modes in the magnetic black brane?
So yeah, you're saying there's nothing up here.
Is that what you see, or?
There's nothing as far as I remember.
Yeah.
No. Sorry, what do you expect in the
I think this is an old story that goes back to Hartnell, Compton, Herzog, and others.
But in the limit of 0 temperature, you say?
No, just turning on any magnetic field.
Yeah.
That should, at the level of hydrodynamics, that gaps out the in-plane velocity fluctuations. They go from being velocity, like shear modes in the plane of the magnetic field to being cyclotron modes. And these guys compute with at least in the weak field limit, the dispersion inflation for those modes should be.
The gap is like 1 is like the cyclotron frequency.
That's right. They acquire an imaginary part, and then they also the two shear modes start to separate. The shear mode says, anyway, they were able to do this in ADS-4. I don't know if anyone successfully did it in ADS-5. In ADS-4 it's very easy because the magnetic field preserves rotational invariance, and the analytically the solution of the magnetic black brane and so on.
Quite a different story, at least technically, because you have these ionic charges, the ionic black hole
But like
solutions.
the physics of the in-plane velocity fluctuations getting gapped is universal. That doesn't depend on the space-time dimension. But okay, that's completely consistent with what you see. You see that the modes that were there at 0 magnetic field at the origin, the complex frequency, may now get pushed away.
Yeah.
All right, so I guess as the last thing I want to say is, our motivation for this, and I think I mentioned this at the beginning, is one thing that you can do with these quasi-normal modes, though, right, they are this kind of near equilibrium analysis, is you can then compare them to late stage behavior of very dynamic stuff. And so we compare this to these simulations that Yaffe and Fubini did, and you can see that in both of these cases, when they have a charged plasma and a magnetic field, that the quasi-normal modes that they get are in very good agreement with what we get also. And yeah, I guess as a final statement is one thing that I realized on Monday-ish is, in the magnetic case, I already showed you explicitly, there are these log terms. And so we probably should have been smart and subtracted those off, and we could have gotten a better accuracy on our Quasinormal modes for the magnetic brane case. So that is something that could actually improve this. Yeah, so yeah, I guess that's what I have to this. The final section, this continued fraction section, I think I'll discuss in the solution section, or not the problem section. We'll talk about that. Thanks.
Thanks. You have questions?